Okay, people. Okay, so you've submitted your assignments on Friday or Saturday or Sunday. I haven't looked at any of them. I don't even know if they've all been submitted properly. I'm very surprised to have gotten no emails about problems in submission at all. If there were any, I presume they went to the forum and that Harrison's handled them. He's not got back to me with any particular problem, so I'm hoping I'll see 350 makefiles. So the first thing I'll do is when I get this mid-term paper finished, I will start checking all your makefiles to make sure they all compile something sensible. They all compile, and then I'll have to start, and the ones that don't, I'll have to look at the problems with the makefile and get everybody a puzzle executable and then try to run them all. And that's sort of a big batch processing exercise from my point of view. And then I have to see what kind of test cases to use, and I'll have a long discussion with both Kevin and Harrison, who will be helping me with the marking. So that's the basic strategy. Most important now, though, is the mid-session. You must have had spent some time on the CSE network and just used a local editor and used the DCC compiler, because the basic format of the exam, it will just be, you'll get question 1, question 2, question 3. And each question will be a programming question. And I'll just say, write a hello world program. Okay? Now, that's a bit too simple. That would be even the first year. So it won't be, but that'll be it, something like that. Or maybe, and the more information I give you, I always find, the harder it gets, because you think, oh, I've got to, oh, I can't forget, I've got that, and I've got that, and I've got that, and you start programming, oh, I forgot, I've got, and get all anxious. So the less I tell you, the better. So I'd like to be able to just say, write a hello world program, and you know what to do, kind of thing. But of course, it'll be a bit more than that. But it's that kind of thing. I won't ask you any theory, so I won't ask you for the complexity of some kind of algorithm, or show you something and say, and ask you to write anything, so we know English as such, just programming. All I want to know is you can program. And I really want you to know, actually more important that I know, is that you know. So a lot of you, or a fair number of you, will be under the illusion you can program, but certainly in the exam situation, you might find yourself struggling, and you need to know that right now, and not in week 7 or 8. Okay, then it's far too late to do anything. As far as I'm concerned, learning to program is just like learning how to play the piano. You just got to do it a lot. And you should be, and I told one student who was wondering what he could do at this stage of the course, feeling anxious about their ability level, and I said, decent programmer, at a certain level you could say, needs to write between 50 and 100 programs. off the top of your head. Not just look at a book and copy and paste them or write down what you're reading, but out of your head, top of your head, you have to be able to write down 50 to 100 programs. When you've done that 50 to 100 programs in C, really after that, you get in the exponential curve where you can do just about anything. It really starts to grow. But you've got to get that basic 50 to 100 programs. 100 for those that are struggling and have maybe done too much Python in their life and have a lot of trouble not thinking about Python or thinking in the Python way. Those that know less sometimes are quicker to learn the C because that's all they know. They say, oh yeah, this is how you do it. Oh, okay. So they're not handicapped by knowledge. So in some sense, knowing something can make it harder for you because you always relate back to what you know, and that can hold you back from learning the new stuff because you want the familiarity, and it just upsets you in some sense, confuses you when you don't see what you want to see. So, but that's by the way. The seating allocation is out, so I'm not hearing too many complaints at the moment. There will be 3 sessions, as you've seen. The first 2 sessions actually get seats allocated, 320 into 420 sessions. The third session, you'll be corralled. This is all done by the school. I'm not responsible for this, so this is a tried and true method. This number of students, a certain finite smaller number of terminals, and we have 3 cohorts, 3 sets of students going up and doing the same exam. I think. I've got plenty of questions. And certainly at this early stage, it wouldn't be too hard to get people to be writing different versions of the same program. So I'm even thinking about maybe changing things slightly, but that'll add to our marking. So we'll have to work out whether that's worth the effort. There'll be no lecture on Thursday. Just to make sure, because it's crazy. We'll have a lecture on Thursday. Nobody will be here. They'll be talking to an empty room, I suspect. And in any case, you don't want to be listening to me. You want to be just fine-tuning your skills on the Linux system. Just making sure that you can, off the top of your head, write a little program and that can read from the command line or can read from standard in and print something out. Okay, and if there's something happening in between the two, reading and writing, that's good. And that's a separate problem. And that's the way you program. How am I going to read? What have I got to write? And what's going to happen between the two? Okay. And the first port of call, and C is the real hassle, is the command line and standard input processing. Whether you use A to I or S to F or whatever what you want to use, or get char, it's a hassle. And people think, oh, it's horrible language, but it's one of the language I'm very familiar with, Dutch, has a problem, and people say that, English speakers say that, and maybe it's the same with other language. The simplest words, just congratulations or well done, all these simple things in Dutch are really hard to say. They're complicated words which are impossible to spell, and they're really that long. A lot of the Scandinavian languages have that too. You've got to get past that simple stuff where you think, well, there's greetings and all the things I want to say really simply, and they're hard to say, that's not fair. And you think, oh, it's going to be even worse when I get to the hard stuff, but it doesn't get harder, it gets easier in fact. It's just the way it is that there's a hurdle to get over. And when you get over the hurdle, it becomes plain sailing. Okay, so practice those command line things, the inputs, know how you can print stuff out, and you should have no problem in the exam at all. You find it quite easy. Not that I've set the questions yet, which I've still got to do that this week. Are there any questions about that on the midterm? Anybody want to ask something? One of the questions you should be asking me, what's going to be examinable? Yes? I have no idea how many questions at this stage. And really, it's a question which is not so much it's not applicable, but if I said 10 questions, you should be happier than if I say one question. And one question would mean it's going to be a doozy. And you're going to have to spend 2 hours on it, and if you stuff it up, you're gone. It's all or nothing, all eggs in one basket. 10 questions, you can at least expect half of them to be reasonable and you've seen them before kind of thing. Okay, so the more the merrier, that means they're really simple. how many questions can you do in 2 hours? Maybe 4. If there's only 3, they'll be on the slightly harder side. If there are 5 or 6, that means that you can say, oh, this one's going to be a bit messy, I won't put too much time in that and concentrate on the others. Give you some options. So I haven't really decided yet, because that's related a little bit to what is examinable. And I've been looking at the material and thinking, yeah, where do I want to draw the line? And I think I will draw the line at complexity the complexity lecture that I gave last Thursday, which I'm going to finish off today. I'm going back, I've just changed some of the notes, mainly to do with binary search. So that's all examinable, but again, I'll tell you, there's no theory, so I'm not going to ask you what is the complexity of this or that. Okay, that's something for the final exam. This exam, programming skills. Get used to the environment, be on top of that so that all of that's out of the road, so when you come to the final exam, then it's only the material. You'll have done the mid-session, you'll know what the environment's like, you'll know what you do and don't know, what you hate and what you have to work on. Okay, so number of questions we don't know, but I hope there'll be quite a few. It would be nice, but I don't think I can do it, to give you some choice. Something like that they'll all be the same number of marks and you're only expected to do 5 out of 6 or something. That would be very nice, but I don't know if I'll do that.
Will it cover today's lecture? Will it cover today's lecture?
No. Yes, no. Yes, the finishing off from last Thursday. I'm just going to repeat. So if I look at the lectures, you'll see that last Thursday lecture is here, program analysis I called it, complexity. It's going to let me in. Yes. And it's more or less the same. I've cleaned it up a little bit so that you got on the contents, believe it or not, is I'm using that a lot more these days than I've ever used it before. And what I want to have a look at now is section 6 on logarithmic complexity. I've moved the binary search stuff in there. I'm sure you've all done binary search. It won't be new to you, but I want to do it slightly from a complexity point of view. Not so much from the algorithm itself, that's irrelevant. But I do warn you, it's certainly examinable in the mid-session, but it is expected, I expect you, and you could say this is a rule of thumb, in this course, to be able to program a binary search in 5 minutes flat, from scratch. Okay, that's the level. You should have, say, if somebody says to you after this course, write a binary search for this data, you should be able to do that in 5 minutes. Okay, that's the level I expect as a sort of a minimum level. After that we can talk about all sorts of complicated tree algorithms and structs and all sorts of things and priority queues and stuff. But that's the extra stuff. The basic level of the course is you should certainly know what a binary search is, and I just well expect that you would have done that with Eric. You can program it in C, 5 minutes, and you know the complexity in and out. Okay, that's a basic level that you must have in this course. So, from that point of view, this is at the heart of the course. I mentioned it last week, and it came at it and said, look, don't worry about log 2, log 10, and log E. And I said they're actually all basically equivalent from a complexity point of view. They only differ in a constant. You can convert one to the other by multiplying by some constant factor. We know that that doesn't affect the complexity at all. What I've added now is I've dived into the binary search. It only works for a sorted list, of course. The whole idea is that you can separate, you can determine what you're looking for or what you want to do in either the first or the second half of the list. And when you work out, and because it's ordered, you can say, well, it's got to be this half or that half. If they're not ordered, of course, you can't possibly know that. So we need to know which half, therefore we need to have a sorted list. And in that half that you think, there's my problem, there's where I've got to work on, you apply the process again, you halve it again, and you keep on halving it, assuming you're looking for a particular element, you keep on halving until you have just one element. And if that one element that's left is not the element you're looking for, you know it's not in the list. So that's the basic philosophy or strategy of the search algorithm. People do call it divide and conquer. I don't. It's controversial. The problem with divide and conquer is in divide and conquer you divide the big problem into two halves. And the two halves, each one, the amount of work required is a lot less than half the big one. Okay, when you halve the size of the problem, it's actually a quarter of the amount of work. So every time you reduce the amount of work by a much bigger factor, then you reduce the size. You reduce the size by 2, you reduce the amount of work by 4. And when you work that out, that ends up being logarithmic. You really save yourself a lot of work than if you try to solve the big problem. The problem with binary search is, while it's not divide and conquer, you only look at one half the problem. You may be in the first half, then in the second half of the first half, and the first half of the second half of the first half. So you just narrow it down, but you only actually ever working on one small part of the total state space that you've got. The number of inputs you've got, you only have to look at one very small part. You're not doing the whole lot. So in a sense, it's not really dividing it all up and conquering it all. You're dividing it all up, just conquering a little bit of it. But okay, that's almost a philosophical question. So here's the algorithm. There's nothing much to say about it. You take an array at the top very quickly. Again, you need to be able to do this. So from today, you can say, well, when I get home, I'm going to have one practice go at it, and I'm going to keep on practicing it every 2 days until I get it right. Okay, that I can just write it down without thinking. I can close my eyes and write it down. Okay, that's the level that you need to be, certainly. And if I don't ask you binary search in the midterm exam, chances go up it'll be in the final. And it may not be exactly binary, it may be some modification of it. Okay, so be very aware that this is important. Okay, so we have an array coming in, it has a size, and we have a key that we're looking for. And we assume that we haven't found it. It's the same as I've kept the same style as the linear search. Assume you haven't found it, and if you have found it, you set it to 1. I could use STD bool and use true and false instead of 0 and 1, of course. So I assume I haven't found it. I start with low and high being the bounds of the array, and then I check that I haven't found it yet, and that low is less than high, and I take a midpoint and compare the midpoint with the key. And depending on the value, if it's less than or greater than, I change the low or the high accordingly. So if the midpoint equals the key I'm found, if the element at mid is less than the key, then I'm on the second half, so my new low is mid plus 1. Otherwise, my new high is mid minus 1. So I'm working on the first half. Conceptually, it's very simple, but when you've got to do it with no help, no references, you've got to be a little bit careful you don't get something wrong and you get the less thans and the mids and the highs, because you've got a few variables floating around there. So it does need practice. Okay. Point of this lecture is certainly not to go through the code. Point of this lecture is what makes it so spectacular, something so simple. Binary search requires input to be sorted. It requires an ordering comparison. Linear search only requires an identity. There's a subtlety there, which is, for database people, more important that you actually, with binary search, you're comparing values, 2 different values. And that sounds easy when you have, and is when you have 2 integers, but you have 2 complex structures, and you're comparing 2 multi-field data structures. Then comparison may be a difficult job and may certainly be timely, expensive in terms of time. So using comparisons rather than identity can make a difference to the complexity in particular applications. The other thing that's particularly significant is that linear search is exactly that. It's a linear search. You start at 1 because it's not ordered. You go to 2, 3, 4, 5, nicely in order. Linked list order, almost, or linked list style. That means a linked list is a perfect thing for linear search. With binary search, you do that with a linked list, you've got hell of a problem, because you have to be able to go into the middle of the list. There's no way you get to the middle of a linked list without cheating in some way. You've got to step through them and work out where the middle is, and then you've got two halves, and then you're going to have two starting points, and you, well, okay, that's now the first half of the list. I've got to free all that if I'm no longer interested. I'm only interested in the second half. So you've got a lot of work to do just to get to the starting point of the part of the list that you want to look at further. So everything's sequential, but binary search is almost arbitrary. It's all over the place. You're there, you're there, you're there, you're there, you're there, you're there, that kind of thing. It's got to be randomly accessible. So an array is perfect. Okay, so the basic data structure for binary search must really be something, well, it's got to be random accessible. And usually it's just a simple array of structs. So there's a major difference. So in a sense, you could say that binary search is fussy. But it really pays dividends, because if you have 10 billion records, then linear search requires you to look at every single one of them to find the one that you're looking for, and if it's not there, you do the whole lot. Whereas binary search, you halve it, you halve it, you halve it, you're halving it continually, and in just 35 steps, you'll get down to 1. Okay? The difference in number of comparisons is 35 against 3, 6, 9, 10 zeros. It's massive. Now, just think about it. I mean, that's obvious in a way. But in the old days, some of you maybe, when we had a telephone book, Sydney telephone book, it was that thick. Now, if I'm looking for somebody with surname Zanzibar, I don't start at A and then start looking for Zanzibar. Zanzibar, A. Okay, next page, A. Next page, B. Now, that's not the way to look at the telephone book. What we do is when we have a long list and we know what we're looking for, we say, oh, it must be, maybe it's in the second half because it's a P. Yes, probably up. You go to the middle, you open the book, no, it's to the right of that. Okay, halve it again, or some proportion, and in 35 flips of the pages, you'll find your telephone number or surname or whatever it is. That's how we naturally work. Now, of course, on the internet things are different. You just use a search algorithm, get it to do it for you. For the old days, we all did binary search as human. And so that 35 is fantastic, and that's all we're doing on the computer. Now, the complexity, where does logarithm come from? You've got to know this. You can't do data structures and algorithms course without having done complexity analysis or understanding it and being able to reproduce it half asleep. It's very simple. All we're doing is we're halving things, and that more or less almost tells you what you need to do. After K page turns, or K iterations, K times finding the mid, and then choosing a half of the set that you've got, the array that you've got, or the array section that you've got. After K operations of finding mid, you will come down to 1. So each time you halve, so after 2 to the K, in each operation you halve the list, so 2 to the K changes will bring you down to 1. So 2 brings you the length to a quarter of n. K iterations, you will have 2 to the kth length of list, which is going to be 1. So in the worst case, if the element is not there, your kth iteration the length will be 1, so n to the 2k, n divided by 2 to the k will be 1. You then have to do a little bit of mathematics where you simplify, you multiply both sides by 2 to the k. It's very simple. Then you take a logarithm of both sides, you simplify by, when you've got a power of a log, you multiply that out the front, it's a multiplier, and then because log a of a is 1, you simply have the expression k equals log n. Okay, very simple, little bit of mathematics, all coming down from the iteration, where for every iteration you halve the size, or halve n, halve the size of the data set. So that little computation there, you must know. And that's a simple little question I could ask. I won't ask you that question guaranteed in the midterm because again it's programming. Okay, we went through the big picture stuff before. I did all that before. I've not changed anything there at all. I just cleaned it up, some of the English. Oh, that's where I finished up last time with the 3 different ways of Fibonacci. Fibonacci iteration, which was extremely fast. Fibonacci recursion, which was very slow. And if you remember, with Fibonacci iteration here, it was negligible in terms of time. It's so fast. With recursion, we did a huge amount of repeats, number of repeats. In fact, you see even with 30, number of calls of itself is more than 2 million. The time, you saw it in the time, Fibonacci of 30 was still fast. By 40 it started to slow down, and by 44 it was a terrible time, 13 seconds. And there you see the plotted numbers. I plotted them, and you see the exponential behaviour. And that we could get rid of that exponential behaviour by using dynamic programming. And the basis of dynamic programming is just simply give it some memory. It's called memorization, and it actually, well, I call it a cache. It's just an array which stores all the values it's computed as it's calculating them. So it never throws anything away. So when it's stored values, if it needs a value fib of an earlier number of a lower order, it can just pull it out of the array it's got. And that's the point of that little cache here. Line 25 to 29, you see cache 0, cache 1, initial conditions, and every other value is given -1 as not being defined. In the actual algorithm itself, line 15, you see the cache is being affected. It comes in, it will give you a new cache value for every value of n. And the n-2 value will have already been done. So, that's not something I would expect you to do off the top of your head, by the way. That's something you would need to work out because that's non-trivial. There are a lot of little things going on there. A lot of housekeeping. Okay, I think that's... Okay, and now we go on to the actual... Is there something else I was going to do today? Before I go on, I've opened up the solutions to week 4. I went through week 4 as well. And week 4 is examinable. Okay, so the exercises here you should do. Then that includes, for example, the QUAC data structure. I'm not saying I will ask you this, but a question would be, I would provide you, for example, a QUAC ADT and ask you to write another routine. Won't be CUSH, that's a bit too easy, but could be some kind of other operation which is like push or CUSH or pop, some other operation. Then I would ask you to write an operation, add it to the QUAC and test it. Okay, with some applications, very simple application. That would not be an unusual question. It's a way you can ask questions on stacks without asking you to... There's no way I can ask you to write a whole QUAC, the interface and all the functions. It's ridiculous. Okay, what you need to do though is, and it's, when I do ask you a question like that, it's actually not that hard. You think, oh my God, it's a lot of code, but all that code gives you an awful lot of help. You can see how all the pops and pushes and all the things are done that I give you, and you just have to add something. So it's actually much easier than it seems. Okay, that's 4. So, and I've opened up the, so you can, I thought I'd better open up pretty quickly. Where am I going? Here. Otherwise you won't be able to see what the solutions are. So here are the solutions. Okay. Now, tonight's lecture is slightly confronting, I think, for some of you. Will be. Don't tell me, it doesn't let me in. Oh, that's right, because I haven't opened it up yet. I think that'll accept that. Okay. Subset construction. I spent a good part of the weekend on this when I should have been doing your exam. That's the reason the exam isn't done yet, because I got sort of involved with the subset construction, and I was looking at last year's and before that, and I thought, that's the way they've done it, that's the way he's done it there. Not theoretical, but it's sort of halfway between theory and practice. Bits of program, some explanation, but I wasn't very convinced that it was understandable. It just didn't give me enough base. So I've given you here, no question, too much base. By that I mean I think I'm going to overload you with how you can do this different ways with different aims, which will probably in some sense confuse you, but you'll still have to pull out it's actually the same thing happening, and it's just a repeat of the same approach, 3 ways. And that, I think, when you start to see what the kernel is in each of the 3 algorithms I show you, you'll say, it's actually quite easy. And then I think you get on top of it. And then you could almost reproduce it without thinking, because you really will understand, while they're different things, they're still doing the same thing. They're achieving different results, they're still doing the same basic thing. Okay, what's the issue here? And could well be that you've had this in 9021. Doesn't matter, I'm sure that Eric won't have done it like I'm going to do it. What are the subsets of a set? And here I have a set X, Y, Z. They're just numbers, and I want all the subsets. Now, of course, on the very right is the normal way you do it. X, Y, Z, that's all 3 elements are in the subset, and then you'll have X and Y, then X and Z, and Y and Z, and then you have X, and you have Y, and you have Z, and you have nothing. So there are 8 different subsets, including the 0 case, which is sometimes not considered a subset, the empty set. That's the right way of doing it, the right-hand side way of doing it. On the left, it's going to be the way we do it, and that is the way you need to think about it for this lecture and for the code. And you'll see why it'll look bizarre, and you'll think that doesn't make sense, and why does he do it so weird? There is a subtle reason, and it would be nice maybe to actually reprogram it so that it does it slightly more intuitively on the right. But I'm happy with it as it is, and you'll know at the end of the lecture whether you're happy or not. And on the right, you can see what's actually happening here. And if you really see what's happening here, you'll have a hell of a head start on the algorithms, because all the algorithms are doing are that thing on the left. Just calculating the subsets in a particular way. Now, what's happening? The first, we start with them all. X, Y, and Z are in the subset. Fine. And then we say, well, Y and Z, and then we say X and Z, and then we say Z alone. Okay, now we go on to the 5th subset, which is X and Y, and then we go on to the 7th, being just X. Now what's happening here, first is we're going right to left. And what we say first, and the mindset is, let's assume we've got the most right element, the Z. Now let's assume, and let's go back 1. And we may or may not have the next element. If we have them, we've got the Y. And let's go back 1. We may or may not have the next element. x. Oh, we've got him once in number 1, and number 2 we haven't got him. Now we're finished with the y case. Now we have the case where we've still got the first element, which is the last element, z. We've still got the element z, but now we don't have y, and we may have x or we may not have x. Okay, now we've had the first 4 cases that way, and now we say we've got no z now, and we do it again. We have y, 5 and 6, and we have or have not got x. Or we don't have y, and we have or don't have x. Okay, so that's really the clue. When you really get yourself thinking backwards, why would one want to think backwards? But you need to think backwards here, and I'll tell you in a moment, I'll give you a hint why it helps. So we have z, or we have not got z. The next level of recursion is we've got y, or we haven't got y. The next level of recursion is we've got x, or we haven't got x. And if there was more, we have or we haven't. We have or we haven't, deeper and deeper, where depth is are the elements of the array, the numbers in the array. Every time you come back 1, you may or may not have that element. May or may not have that element. That is the algorithm. That's almost the end of story. And everything you're going to see tonight will be may have or may not have. And that's what you're going to implement. And when you understand that, that's what it holds it all together. It'll all make a lot of sense to you at the end. Now, why are we going right to left? Well, to be honest, I haven't tried it going from left to right. There's one reason why right to left is actually not so simple. If you start at 0 and you recurse up, where do you stop? Well, when you get to the end. Where's that? Well, n, whatever that is. Oh, so I've got to, every time I iterate, I've got to pass my n value through so that at some point, my recursion knows when to stop. It must know what n is, otherwise it can't stop. It has to have the base case, which is n. Now do it the other way around. Think about it from right to left. If I go from the top, I start at the end. Now where will I finish? 0. You don't need to tell the program to stop at 0. You don't need to pass 0. So the first level of recursion is n. You just say, okay, bang, handle the n case. And what does the n case do? Oh, break it up, n minus 1 case. It got n, goes n minus 1. So that one parameter goes through each time, decreasing, decreasing. Where does it stop? I know where to stop, they all say. 0. Because it can just be 0. Okay, we always go back to 0. Now, of course, if you're going to do segments and funny things in this complicated algorithm, you may have to have a starting point and an end point. If you're doing some kind of merge sort or something where you're actually doing a piece, of course things change. But in the application we have here, where we necessarily and naturally want to do all the subsets, that means from top to bottom of a fixed array, it's easier to start with an endpoint and decrement that naturally in your recursive calls. You always have to give it at least one parameter, otherwise you haven't got a recursion, you've just got an infinite loop. So the only parameter you need to give it is the next step. Otherwise, again, if I say it again, if you start at 0 and let it step up, you have to give it the next step, which is n plus 1, and the endpoint. You need 2 parameters. And every time it looks to see whether it's at the end yet. Oh, it's not there yet, so next level of recursion. Am I there yet? No, not yet. Another one. Am I there? No. So all that little, am I there yet? Go another one. Doesn't have to happen with 0 because, well, it does, but it doesn't happen with 2 parameters. It comes with 1 parameter. So it's slightly easy to implement. But it does require you to think backwards. Okay? And that's what you're going to be doing tonight, thinking backwards. So that's the algorithm here. You start with the empty subset. Okay, we've got a set of numbers, n numbers, and in this particular case, if A2 is in the subset, for, I've made a sort of pseudocode, this is the mine set, for A2 in subset and A2 not in subset, we, for A1 in subset and A1 not in subset, we, for A0 in subset and A0 not in subset, we print the subset. That's it. That's the algorithm. That's the intuition. That's the logic. That's how it works. And what's it do? Well, let's just take the starting case, if you like, the first case. A2 in subset. Okay. A1 in subset. Okay. A0 in subset. A0 in subset, that means we've got X, Y, and Z. We print X, Y, and Z. Now we're in the inner do loop, in a for loop, and now A0 not in subset. Oh, not X, Y, and Z, oh sorry, not Z, Y, and X, but Z, Y, and no X. That's the second case. And now we'll finish with the for A0 in subset and the inside loop. Now we go to the middle loop, and now we said, well, we had A1 in subset, now we're going to do A1 out of subset. So it's now going to be still with the Z, but now we're going to have no Y, but we're going to have X, which is A0 in and out. It's so simple. I've seen that nowhere else anywhere on Google explained that way, but that's just a simple, succinct way of representing the computation of the subsets. We can achieve this recursively by calling a function with decreasing n. So what it calculates is, and when you expand that, blow it up if you like, it's those 4 loops having 2 values each. So it's 2 cubed. 8 different, what would you call, 8 different prints are happening. 8 prints are happening, all with different combinations of Z, Y, and X. And here are the results when you do the algorithm. If you actually run it, if you like, or in your head run it, you get A2, A1, A0, A2, is it A2, A1? Is that right? Yeah, A2, oh. Did I make a mistake there? No, I did, right? I'm forgetting. It's A210, not 321. It's A2, A1, A0, A2, A1, A2, A0, A2, A1, A0. So you get that ordering. Now that ordering again, if that, I hit you with that straight off, you would say, what a strange ordering. Where the hell does that come from? But now you should say, oh, it's easy. Just got to think backwards and turn them on and off. That's the trick. Go backwards and turn them on and off. Get that actually in your head, and print that on your head, you'll find it a very easy lecture. So, how do we turn them on and off? We have our array of numbers, but how do you turn things on and off? Implementation. I have a little array, which if you like mirrors, shadows. I should have called it shadow, would have been a nice name. Shadow's the main array, and it has booleans in there. I called it in. And when an array element is on, the in element is on. True. When the array element is off, the in element is 0, false. Simple as that. How many subsets are there? Well, we know, 2 cubed. That's it. Here's my little program. Now, forget the print. Look at the main first to get a feeling of the landscape of what it all means. And we see, I really did this simply. I don't want any command line stuff. I don't want any standard input stuff. I don't want any rubbish hanging around confusing things. I've just hard-coded 5, 6, 7. They're my 3 numbers, and I want to print the subsets. So the subsets will be 5, 6, 7, 6, 7, 5, 7. Now I've already lost. Thinking backwards is not that easy. I'm sitting in front of a lecture. So 5, 6, 7 are my 3 numbers. Oh, that's a little trick here, which some of you might like to learn or adopt or use. Some of you may know this, the more turned on, the more tweaked C programmers. But you see here I've got an array 5, 6, 7. There's no size, there's no hash defined to say how long the array is. And normally you put a hash defined len 3 or something. The number of times I've changed an array and forgot to change the length and for the program to go weird And the way you get around this problem of not having to change the length of the array, but you can actually change it in, you say, okay, I want to test something else now, so you put different values into the array and recompile it. You don't want to muck around with I/O. You just have this line here which just says take the size of the array and divide it by the size of the first element. Okay? And in bytes that will give you the length of the array. Now that number n is basically a hash def, which could have been a hash def in the normal circumstances. So I've avoided one hash def, and I now know that if I change 567 into something that long, the size of command instruction now in 37 will tell me how big it is, or the program will work out how big it is. It's a very useful little line. I have used it many, many, many times. Okay, so, and now I've got my shadowing in Boolean array, which has got to be length of that size. That's fixed now. I don't have any housekeeping to do. The compiler will sort it out for me. All I have to do is 567 or 10, 12, 95, 3, 4, any length, just plug them in and run it. It's easy. Okay, and reasonably foolproof. It's so easy to be a fool when you program. Okay, so that's all the minor programming stuff. And line 40, of course, is where life really starts. We call subset with A, that's our array, length n, and with our shadowing on-off in array, which is also length n. Okay, two arrays, two lengths n. Now, there's a difference between those two n's in the sense that they will have a different life. And you'll see that when you look at, I'll move it down a little bit, the subset, the actual algorithm. You see there, the two arrays come in, there's A, and I've called it still Boolean int, I kept the same name, and the two values len and n. I call them different names there, deliberately, and you see the comment so that I don't forget myself. When I was programming, I said, oh, what are they doing? Why am I having twice the same n going into it? Why don't I just have one? Well, the first one gets decremented because I'm actually counting backwards in my array. n minus 1, n minus 1, n minus 1 every time. And you see, when I do the recursion, line 27, line 29, n minus 1. That's where it's going backwards. As you must be thinking now, backwards. But the second n is, I call len, give it a different name so that I know what's going on. It doesn't change. While I do want to go backwards, turning off array elements on and off, in effect going deeper into the recursion, I don't want to change, of course, the length of the array in. That stays the same. Now I use that when I print it. Printing the actual subset, when I get to 0, the base case. When I get to 0, I'm finished. I've gone all the way through, turning it on, off, on and off, on and off, on and off, on and off, and on and off. And when I get to 0, I've reached the end of the array, and everything has got a value. It's like going into that the 3 for loops that I showed you in that pseudocode. For A2, on and off. For A1, on and off. For A0, on and off. Now it's being done by recursion, where I'm calling the subset function with my A and the index which is going to be turned on and off with, and that's really, really important, 26 and 28, I'm actually turning them on and off. So I'm turning an array element on or off. The array doesn't change. I'm not zeroing the array. The array is being left alone. It's just a constant. I'm only turning them on and off in the shadowing in the Boolean array in. Why is that important, or how does that work then? Well, when I print it, it's a little bit messy to print. That's why I pulled it out. When it was in there, it looked messy. But when I print it, I print an array, and I get the shadower, the in array, in, with its length, and I just go through it And if in is on, I print the A. If in is not on, I forget about him. Can't be simpler. It's, oh my goodness gracious. Siri is so simple. You see what it's doing? That print is really simple. It looks messy, and I'd like to forget about it really. I wish it wasn't there. I wish it was a nice way of doing that. But the in tells me which array element is going to be in that partition. Partition in that subset. And the subset is only known when I get to the 0, because I start with the top element. I've got to turn him on and off. I first start him having him on, and then I get the next element. That's got to be on and off, but I first start with him on. Then the next element down, he's got to be on and off, but I start with him on, and I work all the way down. But in the recursion, you can see here, I call with them all on effectively, n minus 1, so the first one will happen. So all of these subsets will be done first with them on. So you get the x, y, z, if there were just 3. And then the middlest one, the last one, the very last one I should say, which is the first element, will be turned off. Okay, and then that will be the second subset call. But then we come out of the recursion, and then we go into the next level, and the higher level, which is effectively the y in x, y, z, in the next one up, we turn that off, and we come back in here into this, and we turn it on again, the x1. So the x is turned on again and off again, and then we go back. So we're going backtracking up and going back down again. As we go up, we're finished, if you like, and when we go down again, we're turning them on and off again. So we're doing every possible combination, which is all that the subset algorithm does. So when you see all that, okay, it calls itself twice. Okay, we saw that subset. Both times are the same index, n minus 1, that's the recursion, and with the in, true and false. Very sweet, very simple. Oh, can't go wrong. To be honest, when I programmed that, it worked straight away. I was amazed. I couldn't believe it worked. Sometimes the program is smarter than you are, the compiler, it just worked. And I thought, oh, this is too simple, it's too easy. But it worked immediately. I didn't have a single error in that, because how can you make an error there? I mean, as long as you've got n minus 1, you're working on it, you're turning it on and off, and you're calling it so that the next level of recursion is coming backwards. I say deeper, but I mean coming back in the string or the set. So I explained that a little bit here. It calls itself twice, corresponding to the left and right branches. The left branch is true, and the right branch is false. And at 0, we're done. We have a complete subset. And now, the only thing is I'll say here, I've got a bit of debug in line 20, which is just, I had to convince myself it's actually doing the right thing, because it came out with the right answers, but I thought, is it just, am I crazy? Is this really working straight off? No problem. So I put the debug in there just to see that it was actually going in different values, that n minus 1 was actually happening, that I didn't have iteration in there, it was pure recursion. It's completely recursive. So I checked the value of n going in each time just to make sure things are working. So it's really debug, and I've left it in there. So you see, I ran it, I compiled it, I ran it, and it comes back with all of the down, 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 just like the Coles advertisement. n equals 3, n equals 2, n equals 1, then n equals 0, wacko, n equals 0, 5, 6, 7. Then it comes out of the recursion, and it's 0, then it goes back in, it turns off the 0 element, if you like, and then it does the 6, 7, and now it's coming up again, and it goes down again. It works like a treat. Sometimes, and even I look at it, I have to look at it twice. I just did this, what was it, Sunday. But this morning when I looked at it again, yeah, that's right, that's working. But it's just something which comes natural even to me. Haven't seen recursion a lot of times, and just have to look at it twice to realise that it's sort of iterating through the array recursively. And maybe that's the problem I've got to hang up a little bit that makes me hesitate. Is it really working? It really is recursing simply to iterate through the array. And it turns things on and off just by that shadowing in array. Okay, they're the factors. You can actually draw a picture of it. I've got 100 different graphics packages. I could have done it really pretty, but I was testing it with so much input and didn't know how big the tree was, and in the end I said, oh, stuff it, I'm just going to do it ASCII. So I just do some backslashes and forward slashes and numbers just to get it down right, and if nothing changes and I don't change anything, then I'll actually draw a pretty picture of it. So you can actually see here, n equals 3 at the top. There are 3 elements in the array. Okay, so the first thing is we call the array, sub I called it, A3 in 3. That's a very call in the main program. Okay, and then what actually happens, the last element, 5, 6 and 7 were in the array. The third element is 7. 7 is going to be included or it's not. Plus is included, minus it's not. Then we get to the next level of the recursion, n equals 2, the first call in the recursive routine. I've called it once and it breaks it up into 2. With the 7 first, and later on it'll do it without the 7. Now, with the 7, it now breaks it up into with the 6, plus, or without the 6, minus. And when it's decided, well, the first time through, it's got 7, it's got 6, and then it can have 5, or it can't have 5, whatever it likes. Well, it needs both. So you see here 5 plus and no 5. And if you've got 7, 6 and 5, well, you've got 5, 6, 7. So easy. And if you've got 5, 7, 6 and no 5, well, you've got 6 and 7 and no 5. So all I'm doing here is reading the path. So if you read from top to bottom, the 7 at n equals 2, if I don't have a 6 and I don't have a 5, then I've only got 7. Okay, and if I go to the very right, and I don't have a 7, and I don't have a 6, and I don't have a 5, well, I've got the empty set, I'm afraid. Got nothing. That's all there is, 7, 6, 5. So is that little binary tree. Now, what's the complexity of that? How many nodes are there at every level? 2 to the power n. 1, 2, 4, 8. 8 at this level. 16 next level. 32, 64. Gee whiz, that looks very exponential to me. It should be less than 10 seconds for you to see that's an exponential tree, if I've ever seen one. So it's going to have terrible performance. Do I get onto that? I have no idea. Number of paths equals the number of leaves equals the number of subsets is 2 cubed. Makes sense? 3 booleans, all 0, 1. That's the in, so the 0, 1 saying it's in or it's out. 2 cubed. So really this whole exponential business, it's so obvious now. Why didn't I just say that at the start? Because if I just have an in, and everything can be on and off, so there are 2 possible values for every element of the array, which is length n, so 2 to the n. That's exponential. End of story. So obvious. It's so easy to understand now. Oh, now that I see the in and how the in works, it's easy to see why it's exponential. Because the in and the out, or the in, on and off, is the only thing that determines what goes in the subset. The values in the array do not change. They're sitting there quietly minding their own business. They will be printed or they will not, depending on what the value of the in is. Okay, so how many recursive calls will make? Well, that's a bit more complex, depending on how well you know your geometric series and what the sum of a geometric series is. And do you even know how to spell geometric? I don't know. How many of you would know what a geometric series is? Something is geometric if the ratio is the same. It's not arithmetic, it's not adding 2, if you like, to all the coefficients. It's actually the ratio between any 2 terms will be a fixed ratio. It's the same ratio. So when you double it, so you're going from 2 to 4 to 8 to 16, you're doubling it. So the ratio is constant 2. So the sum of a geometric series up to 2 to the n, that geometric series there, is 2 to the n plus 1 minus 1. Oh, isn't that interesting? And my God, that makes sense, because when I look at my tree up there, you see that there's a 1, the 2, the 4, and the 8. That adds up to 15, which is exactly 2 to the n plus 1, 2 cubed. 2 to the 4th is 16 minus 1. So I've got exactly the right number of nodes. So, but the consequences now you can work out because you know complexity. You say, well, it's now I can work out exactly how big my tree is going to be. And if I have 40 numbers, I'm going to require 2 trillion subset. 2 trillion subsets is what is going to be generated. If I only have 20 numbers, it's only a measly 2 million. So it seems harmless, just 20 little numbers. How big can then, how many subsets can there be with 20 numbers? Can't be that many, surely. Well, yes, it is. When you have 20 numbers, you'll have 2 million subsets. And if every subset has some property or something that you want to look for, that 2 million will cost you some time. Okay, and we haven't even talked about the recursion, the recursive workload here. It's all based on recursion, of course, but that's not the issue at the moment. So the complexity argument, we've already worked out it's 2 to the n plus 1 minus 1 if you want to be exact. Now, that was all an entree. That was all the preparation. What the real problem is in computer science, the hairy-chested, serious computer complexity problem, is the subset sum problem. The question is, when you have a set of integers, we'll say positive integers, or keeping it simple, do any of the subsets total a particular value that you give it? That's the real question in computer science, and that's the problem we're actually trying to solve here. So given a set of positive integers, a set like A, and an integer k, is there a non-empty subset whose sum is equal to k? So if you have 20 numbers and you give it a total 4,327, do any of the subsets of those 20 numbers equal 4,327? That's the question. What's the complexity? What have we got to do? Well, we can generate the subsets. That's why I did it all, so that I would have them, because I need them to do the sum. Okay, but realize where we're going to with this. We're not actually interested in knowing how many there are. We're not actually interested in knowing how many sum to k. We just want to know, is there at least one? Okay, this is a well-known problem. It's a problem that's actually used in various applications, not least of which is cryptography. It's an interesting problem. Complexity of getting this fast is very important in computer science. This question of, is there a subset that has a particular total value, sum? And as long as there's one, you're happy. And if there are 400 of them, that's also fine. It doesn't change the answer. Answer is yes or no. So actually this is a yes-no question, but we can do more in our program, and we are going to do more. So for example, if you have the set 2, 4, 6, 8, 10, and you give it a total 11, is there any subset? And the answer, obviously, you can see, no, it can't possibly be, because that's odd, and all the input numbers, all the array elements are even. So it's never going to be odd. But if I give it 2, 5, 7, 9, and I give k equal to 14, well, the answer is yes, because we know we can generate them. 2, 5, 7 and 5, 9 both sum to 14, so the answer for that array will be yes. So the subset algorithm we have used actually generates the subsets of a given set, all the subsets. So we won't answer yes, no. We won't address the problem properly or exactly. We'll actually do a lot more. We'll actually generate the subsets, and we know what the sums are, of all of them. So how do we modify now? It's very simple. got a great working sub. Can I change sub so that it answers to the question or gives me the sum of all of the partitions and sees whether any of them, of the partitions, of the subsets, if any of the subsets equal the given k, that value that it has to be equal to. And I tell you here exactly what I did. Sunday or Saturday night, Sunday morning, I actually made 3 basic changes. We had a sum parameter, wacko, that's not hard to know, you've got to put in the sum, so you need a value, a number, k. We initialise that in main, that's 1 minute work. We recurse from n, as we recurse from n down to 0, we decrease the sum when we call subset. Now, not only do you have to go backwards in processing that array, you, in this algorithm, go backwards in calculating the sum. So you start with the sum when you first call the subset function. And then whenever you say an element is in the subset, because remember, we still have that in-out business, so when it's in the subset, then we know we have to take that value of that element off the sum. Because what do we want? We want the sum of the elements. So if we've got the sum is 10 and the element is 5, well, okay, there's 5 of the sum of 10. So we've only got 5 left to play with. And if I take another element and it has a value 3, well, there's only 2 left. And if I have another element which has value 6, I'm in -3 territory now. The sum is being exceeded because my subset, as I generate them, as I'm calculating these elements, they could what would you call it? They could go greater than the sum itself. But that's fine because what we're doing here is we're generating all the subsets and basically calculating all the weights. And the thing, and this is what's really crucial here, do I actually say that? No, there's not. Yes, 3 is the crucial thing. I should have highlighted that one. When we reach n equals 0, we're right at the start of the array. We've worked the way on, off, on, off, on, off for all the elements with the in. When we reach n equals 0, if sum equals 0 there, hallelujah, we've found one. We really have found one. Because what can happen, as I just mentioned, when your sum is, say, 10, and the first element we see is 10, well, if there's any more elements in that subset, bad news, because it's going to be under 10. So the 0 can happen any time. But the only time that we're interested in it is when the index is 0 and the sum is 0 at the same time. Okay, so that's those 3 things there. The first thing is trivial, and there's 2 and 3. The 2 I'm going to go into in a little bit more detail when you see the algorithm. So here's the print subset. No change. Thank goodness. I print the subset out based on that in. No problem. Now, the actual subset, well, let's go to the main program. Let's work from the outside in. Well, I see now I've got a k equal to 14. Not hard. I'm hard coding my 14. I don't want I/O problems. And I'm calculating the length of the array the same way. The bools is being initialized the same way. Subset A, N, I, in, N, and K. K's got to go in. Now, we're working backwards. So that way for you probably. Is that left to right? Right to left. It's that way for you. It's left to right for me, of course. So right to left is the way I'm working through the array. And the sum, I'm decreasing. So both K and that first N will decrease in the algorithm, in the recursion, as I work to, hopefully will be a subset, which means a complete subset. I mean all the loops of all of the recursion's finished, so it's reached the front, the end, the start, because it works from the end to the start, and the sum becomes 0. If it goes under 0, it's just bad luck. It's not a contributing, if you like, subset. So, now I look at the subset itself, the recursion, and you see The in and out, the in works exactly the same way. The in is set to be true or false. That turns it on or off, that element. Now, and this is the only thing that requires you to think for a second. Well, maybe a minute and a half, something. Thinking, real thinking is required here. It's not hard thinking, but maybe second year thinking, not first year thinking. And that thinking is, when you have an element in, then you've got the element in. And that means you've got to take that element's value off the sum. And if you don't have an element in it, don't touch the sum. Obvious? If you've got the element in line 28, you see sum minus A of Ni, because A of Ni is turned on. In of Ni, n minus 1, is turned on. So that means I've got that element, and therefore it's contributing. So I'm working out the value will be of my subset on the fly. So when I turn something on, it's going to contribute, and I keep going. Because if you think about it, this recursion, it's working its way down. The only thing it knows when it gets to the end are what it knows in its little world, its little instantiation of that function. It gets some value as a parameter, and it takes off the value of A0. That would be the final act. Now, when it comes in, it could already be negative. It could be a really big number. But whatever it is, it takes off A0, and then it will come in. And if n equals 0, and the sum is 0, wacko, we've done it. Hallelujah. We have our subset. That has the right total. Of course, it happened when we hit n equals to 0. If it happened any other time, we don't care. We actually don't even know. Because at any other time, if we're not at the end, we just continually decrement the subset. If we turn it on, sorry, we don't decrement, we decrement the subset, and we decrement or decrease the sum if we turn it on, and we decrement the subset, but we don't, or decrement the value, the array index, and we don't touch the sum if it's turned off. Now, if you can see in those two lines there, whatever they are, 26 or 27, 28 and 30, they're crucial. What happens to the sum value. That's the trick. And realizing that turning on and turning off the array element has a consequence for the sum, and when you do it, when you make that, when you have them, it's a dance. It's a recursion dance with a subtraction off the sum, and it becomes a dance of the two. And eventually, the climax of the dance is they both finish, and that's it. It's happened. Okay, so DCC, I call it subsum, subset calculation with a sum, A dot out, and it came back with, I took the debug off, was the one thing, you'll see that comment there, I thought, I'll leave it in, because if you want to cut and paste it, you see the n is decremented, the len is constant, don't want to forget that, for me that sort of, so I don't forget what those things are doing, but the printf, I've had too much output is generated. Even when I got 4, I had 15, if you remember, 15 nodes. The recursion, it goes down into the recursion, comes up, backtracking sort of. This is what we don't see really, unless you put the print in. It goes up and then comes down again, it goes up again, it goes down again, up and down, up and down, up and down, up and down, all the way across. And when you go to n equals 4 elements, array of 4, or array of 5 and 6, it blows up. It's going all over the place and you cannot possibly follow it, and the debug becomes useless. For 3, it was doable. For 4, I'm finding it rather pointless. It's just a very long list of recursive statements, which level of recursion is at. And so I just turned that line off, commented it out. And they're the 2 lines it came up with, exactly the right 2 lines. Again, it worked almost instantly. There was nothing wrong with the program at all. It's so, in a sense, it's obvious, it's clean, it's elegant, and this is where I started to get to the end of what you can do with backslashes and forward slashes. And it's not really useful because once you know how it works, this is rather irrelevant. But you can see with the 14, the sum is 14, and whether 9 is in it, and if 9 is in it, well, you've only got 5 left after that. If you take the left branch now all the time, 9 is in my subset, well, I've only got 5 left. 7 is in my subset, bad luck, I'm now -2, I'm in debit. And I've got 5, well, that's getting worse, -7, and I've got 2, -9, no chance. Total's not big enough to use that subset is useless. And then, of course, let's go to the right-hand side, the very right-hand branch. If I've got no 9 minus if you like, then I've still got my 14, and I've got no 7, I've still got my 14, I've got no 5, I've still got my 14, and I've got no 2, I've still got my 14. My sum is 14. So the sum just gets changed by the value that contributes to that subset. And we're only interested in this value and that value, because they both are 0 at the leaf. You'll see at some minus some level, at the one node up, a 0. So when we had 14, with 14 as our sum, when we take a 9, we don't take a 7, but we do take a 5, okay, we get already 0, but we've still got the 2 to go. If we include 2, we shouldn't have, because we go to -2. If we don't include 2, wacko, we're right. Okay, so you can see all the cases have been covered here. An array of size 4, 2 to the 4 possibilities. 16 leaves, what we've got. The last one is no elements in the subset at all, the empty subset. First one is the full subset, and we've got everything in between. And here you can see all the weights. And that little program prints it all out. No, it doesn't print out the weights for you, because all that we're interested in doing, that program, of course, only comes up with the partitions that are the subsets that are 0 have a 0 sum at the leaf. Just to push that point, I can't say it enough, line 20, 21, so 21, 22, 23 are really important. If we get to the base case and the sum is 0, we're finished. If we're not at the base case, we're in here, we don't care what we've got for a sum, we just keep taking off the numbers if we have the element in the set, the subset. If we don't have the number in the subset, well, we don't touch the sum. So we've got the left and right business. Now, I don't know how many times now I've said this left-right business, in or on, off, true, false. Many, many times I've said it to you now, so I'm hoping you get used to it. Okay, so that's what it looks like. Now, the sum equals, sum z equals 0 at an internal node is irrelevant. Sum equals 0 at a leaf node is a solution. There are 2 solutions, reading from top to bottom, 9,5 and 7,5,2. They're the paths. But I've got to sort of follow the line, I've got to conform, I can't be a rebel here. The program or the problem is yes, no. Not 5, 9 and 7, 9, 5 or whatever those numbers are. It wants to know yes, no. All right, that's easy. That's easier than what I've just done, because I no longer care what contributes to the sum. I don't have to know which values. When thinking about it now, what am I doing? I'm stepping through the array from right to left, backwards, and I'm calculating the sum, but I don't care which values are contributing and which values are not. All I have to do is make sure that the sum is properly calculated. Now, this is where I'm going to pull one of the chairs from underneath you. You'll suddenly think, I thought I understood it. Something you did right at the start, and now you're saying, I don't need to do it. and you'll say, I'm feeling now insecure, I'm going to fall. But you won't. You just have to think just a little bit, and you'll realise that what we need to do now is, because we only need to yes, no it, well, actually I could cheat and just leave the program alone and say if I ever print 1, return yes. And because at the moment, the way I did it, and I didn't even try this, is you see that the recursive subset function returns nothing. I'm not even returning anything. All that the recursion is doing is stepping through the array backwards. So I could use that to say, well, if I print something, print a subset, which means I found a subset, I could return a true. And I wouldn't have to change anything in the code, just return values. And return false in every other case. The only time I want to return true is when I really do get to the end of the array, the start of the array, the end in the process, start of the array, n equals 0, and its sum is 0. I know I've got a subset which has the right total, the right sum. Return yes, return true. I could do that, but it's a bit lazy. So what I do is I say, okay, throw out all the stuff that we don't need now. And what don't we need? I've now got a program called sum yes. Okay, this just says yes or no. Is there a partition which sums to sum, sums to k? If yes, then it just reports yes. If there's none, it's no. If there's 1 or 100, it's all yes. Just one yes. So here we have our... Now, the first thing you notice is, the first thing you think about is, we don't print a subset. All we do is print yes or no. Y-E-S or N-O. Nothing else. So we don't have to print a subset anymore. So that function is out the window. Gee, well, that's easy. No sum, no print. Oh, but if I don't print it, what do I do? And here we have the n equals 0 and sum 0 happening at the same time. And what we do is we return value true. What I just said, basically, I found it. Tell my parent. Okay, my parent is the thing that called me. So you now see that subset is bool, not void. It's now going to return to the upper level, and each level will come back. So if anything reports true, it goes all the way up to the top, and you can bet your life, when you get to main, what do you find? If subset A of nk it was just a simple call before, but now it's an if, because it's a bool that's returned, and if it's true, then it prints yes, otherwise no. Okay, so bool is being returned by a subset. Okay, now let's get to the meat of what happens in the middle there, line 17 to 21. That's where we had the turn on and turn off. We don't have to turn on and off anymore. Wow, and this is where I chop your legs away. And you say, wow, can I stand? What's going on? Because you see subset is being called twice, left and right, with n minus 1, the next value down, just as before, but in's gone. There's no in. In has completely disappeared. It's run away. It doesn't get passed. It doesn't get set. You look in main, there's no in. I don't initialize it. In's disappeared. Doesn't come in as a parameter. It just takes a, n, and the sum. In and len, which is what I called the size, have disappeared. Because I don't need them anymore, because all I need to know is the program works. The only reason, and this is what the hard bit is, why did I have him? I turned it on and off, but that on-off was there only because of the print function. I turned it on, or I turned it off. The only place I used in, I don't know anyone noticed that. No one would have said, oh sir, what's going on? What are you doing with that in? Because the only place it's used is in the print. To know what is on, in other words contributing, and what is off. Because there are two things going on here. The recursion is going through the array from back to front and turning it on and off in a conceptual way. But at any point in time, when you are in some level of the recursion, you don't know who your parent is. You don't know if the previous array index, which was one larger, so if I'm at level 3, you don't know at 4, which was the previous one, because I'm going backwards, whether that was on or off. All I know is I'm either on the first call or on the second call. And I don't know that when I'm in the call. I don't know who my parent is. All I know is that I'm value 3 at this moment. And what 4 was, who knows? And 5 and 6, I don't know whether they're on or off. But what I do need to know, absolutely need to know, is that sum is still performing correctly. The sum, if it is in, which is the left branch, still has to be, the value of the array has to be taken off that sum. And on the right branch, the sum doesn't get changed. Now, I think this is in some sense, conceptually, abstractly, this is the hardest thing to understand, that we have now so little left over. We've gone with a lot of information, We've got the in, the sort of two of the legs of the chair. We've got the recursion, or sort of gives us a solid chair to sit on. And now I've just taken away a couple of legs off the chair. And you think, well, how's this recursion now carrying the whole show? How is it now generating the subsets? Well, when you look at the in, you actually can see that the in, while I was turning on and off, the fact that I used len meant that I've got the whole history of the recursion in the in. It was baggage. It was a thing that I took with me in the recursion. So when I was at some deep level in the array, which is towards the front, the starting index, all the previous ins and ons and offs in the in array, they're all there for me because the length of the array was len, if you remember. So I could see them and print the whole thing out. But if I took that away, I don't know what they were. But as a recursion, I also don't need to know. It's irrelevant because it's only there for the print. It's baggage, it's things I'm taking with me just so that I can work out when I'm turning something on or off, what my parents were and my grandparents were and my great-grandparents and great-great-great-grandparents were because I need to know all that to work out what to print out. Otherwise, I have no idea where I've come from. Now, that's the hardest thing probably in this lecture to understand. Actually, the simplest thing, in a way, when I take away stuff, makes it harder to understand. So, the final subset algorithm, 7 to 23, is, well, the sum 0, n 0 is easy. You've got to be at the end of the tree and have done all the elements. That's the easy bit to understand. And the thing, the heart, the beating heart of this program, the beating heart of the algorithm is line 1819. And I call it here with and without. Wout is just, I like to have 4 letters so they can have them underneath each other so they look pretty. Okay, so I've got with and without. And what I do is, the return value is, I take both basically and all between them. So I do the left and do the right, and if either of them are true, true's got to come back. Okay, this is the way I pass that information. It's very common in C when you do have a recursive algorithm and deep in the recursion something is true and you want to pass that all the way back up the top again. Now, if you call recursively with many times, in other words, here we have 2 calls, then I need to, for each of those elements, if any one of them is true, I've found a subset that's got the right sum. I've got to the end and it's the right subset and I've got to pass it back up. Because remember, there's a lot of backtracking going on here, so the algorithm goes to a leaf, comes back up again, goes back down to another leaf, goes back up again, goes back down to another leaf. Okay, now if it finds a sum of 0 at some leaf, when I go back up again, it'll go back down again, but that path, one of those 2 subsums, will actually have yes, or have true. And I can go back down again, and it'll come back with a false. But that's fine because it's an OR. So the true goes up to the next level. And then it will go back down again, but the true gets passed up. So that trick of that OR operator is very common in C. So that's the beating heart of that program. My goodness. All that work, 1.5 hours, basically, or an hour, just to get yes. A lot of work to get yes. So what's yes? Is there a subset of the array 2, 5, 7, 9 that equals 14? What we saw with the other program, the sum sub.c, there are 2. And this program, whether it was 1 or 2 or 100, it doesn't know, doesn't care, just says, there's 1. Okay, just reports yes. What is the complexity of this algorithm? Now that will test you. How many people are smart enough to know the complexity? And if you all knew it, because Eric was just so good for last year, I'd be so impressed. Well, let's do one thing. I'll give you a hint. There's our program. Basically, this is what the recursion is. I showed you, and we talked briefly, or I talked briefly to you, and we talked about what is the complexity of sub.c. And you saw that it was a tree like that. At every level, you doubled the size. 1, 2, 4, 8, etc. We said that's exponential. Now, that program calculates all the subsets of an array. And depending on the number of elements, the tree gets big. And that's why it's exponential. It goes up to powers of 2. What's the difference? Question for you. What's the difference between that program and this program? I'd love to give somebody a bonus mark. If somebody comes up with something really insightful, it shows that they understand. Understand, that's a major thing here. Really, who is really understanding what's going on? What's going on there? What will be the complexity? Contributors? What's happening? Anybody? Do I have to ask somebody? Somebody who's been listening, preferably. Remember, I'll say again what the baseline is. Sub.c. Exponential. Exponential because it went 1, 2, 4, 8, 16. Okay. What's this algorithm? That was sub, and that sub was calculating all of the subsets. What's this tree doing? Showing. Come on. Can you say something?
Maybe it just calculating until it finds the first answer.
No, you're going the wrong way. The tree looks a lot like the other tree. Okay? Let's do this. Show you the other tree. And now we're talking about, you sometimes see those cartoons when you see the same picture twice. And what's the difference between the two pictures? And in one picture, the guy will have a hat on. The other picture, he won't have a hat on. Okay? That's the intelligence test I'm wanting you to pass now. Can you see the difference?
I think it's
okay, here's
you now get a return. So once it reach 0, it immediately terminates.
see where you're going, but you're thinking too deep. It's in your face. Face. So in Australian. Okay, there's my first. You got to abstract out the fact this is n equals 3 and the other one's n equals 4. Now look at that picture. Okay.
The second one has to calculate it at every level. The second one is calculating your total at every single level.
I'm missing a word.
Your sum.
Spot on. The sum. The sum. Where's the sum here? There's no sum in sub. Sub doesn't sum. Sub is sub. Sub doesn't know anything about sum. It's one simple 3-letter word. And when you go back to this program here, this output here, look, sum. Sum. How many times do I have to put sum? How do I put S-U-M on there? It's doing a sum. It's doing a sum. Sub didn't sum, but sub-sum does sum. That's not hard. We can all get our head around that. Now, not only do we have to go down recursively, and we know what that is, 2 to the k plus 1, minus 1. Exponential. But as we're going down, we are summing. What does summing involve? Maths. I love it. Yes, that's extremely good. Summing involves, but okay, I'm going to give you n numbers. What are you got to do when I ask you to sum them? What have you got to do? I hope not. You're the worst arithmetic in the world. Look, 1, 2 and 3, what's the sum? How did you do it? 1 plus 2 plus 3. Where was the exponential here? Or where's the combinations?
The combinations was the previous.
So 1 plus 2 plus 3, what's the complexity of that? 1 plus 2, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is it? Sum. 10 elements, but what is it? What's the sum? What do you have to do? What's the complexity of what you have to do?
Add all the elements.
Yes, but what's the complexity? Yay! Well done! Linear! So I've got to do the recursion, which is going to be exponential, plus I have to do the sum. All these sums I've got to add up. If a subset, if my subset is 2, 4, 6, and my sum is, and the k is 12, 2, 4, 6, I've got to add all three up together. Or in any case, every time, I've got to add up elements. And I've got to do it all over the place. Basically, I've got a linear problem which is on top of the recursive problem I had before. Sub was recursive, so recursive was exponential. The recursion caused the exponential behaviour. But I've got this extra baggage now where I've got to be adding up all this rubbish because the person who ran this program wants to know about the sums. So I've got this linear problem which is on top of my exponential, because the exponential is exactly the same. I'm generating exactly the same tree. It's just the nodes now have the sum built in, and I've got to get that sum by adding up elements. And basically all the elements will be added up many times. But, and so it'll going to be a lot more than linear, but it'll be a constant time linear. It won't be n squared. I'm not adding up every element with every other element. I'm adding up combinations of elements where a particular element contributes to different subsets. So it will be some expression in n, not n squared. So, knowing now that I've got a problem which is made up of an exponential part and a linear part, what's the complexity of some sub? I know what somebody's going to say. I won't fail them. Anybody dare give an answer? I won't ask you. You've taken enough flack already. What's the answer? Who wants to take the risk? and say something that could be very wrong. 2 to the power n was the exponential part. We had that. We've got this extra linear part. That's factor, it's an n. See, it's not a constant thing. It's not 5. It's not 12. Because,
Times that.
very good. Excellent. It's n 2 to the n. I expected somebody to say n plus 2 to the n. So I thought we'd have our first failing student, but no, unfortunately it didn't happen. It's n 2 to the n. That's the complexity of this algorithm. And that's non-trivial. And so here's my... So there was it. The algorithm to generate all the subsets was... What do I say here? With the additional work, I'll say it in some way, just so that we fill something in that, with the additional work of computing sums, which is linear, no, what was I saying? Yeah, I just want to get the English right. This algorithm is O to n. Somebody correct me. Yep. Okay. N times 2 to the n. You all believe that. You don't know your wiki, but I'm sure. But that's. See what it looks like. Yep. With the additional work of computing sums, which is linear, this algorithm is n 2 to the n. Okay, we started with a 2 to the n algorithm. We've now got to do sums, and basically, in terms of complexity, that's extra work, and that cost will be linear load on top of the exponential. In a sense, it's not making much difference. Exponential is so horrible. You know, it's going up like that. The fact of making it linear, multiplying it by n, is just going to mean it's going to go a little bit more steeper. But it's going to take 100 years to do. The fact it's going to take 120 years is rather irrelevant. 100 years is 100 years. So, all right, oh my goodness, so I didn't expect to spend that much time on it. And you know what? I think I will not get into Towers of Hanoi and other stuff. I don't mind spending a whole lecture on this. There's so much in subset summation. You've now seen 3 versions. Okay, the original sub just did subsets. Clean, no problem with summations. Generate your little exponential tree, and you have to get your head around, you're working backwards through the array, and when you get to the leaf, you've done the whole array, and you within know what contributes to that subset and what doesn't. Okay, that's the print, if you like. So you've got a full history. Then we went on to the summation, generating subsets that had a sum. And that was, the difference there was we need to have an extra parameter sum, extra argument sum that went into that recursive routine, and you had to subtract that value from the left call, the first call of that recursive function. Because in the left call, it's included, and on the right call, it's not. And we undressed, you could almost say, we took away a lot of the housekeeping, which in caused, because we used it in the print, we had to set it up, we had to initialize it, sort of, we had to create it, And we had to keep it updated with the left and right branches. I could take that all away because the real problem in computer science, the subset sum problem is yes, no. Does there a partition exist with a particular sum? That's all you're interested in knowing. So I've undressed the algorithm so that it's stripped to basics, and that just says yes or no. When it finds one, it passes the information back up. Okay, it's a nice set of 3 algorithms, I think, or they're very similar. They all have the same heart, beating heart, but there are slight changes in the implementation to get the algorithms to do exactly what we want. Sum or no sum, and yes, no, or the actual partitions themselves, subsets themselves. Okay, so I think I've got to ask you a question about that in the final. It would be irresponsible not to ask you. I have no idea what. I've never asked anybody, this is a bit new. I'm just not impressed by how it's been taught in many places around the world. It's too brief. There's no real feeling for what's going on. There's no groundwork. And for example, just calculating the subsets first, I think provides the groundwork you need to understand what's going on. The sums are nothing. They're just the added thing. And what makes them really nice is in terms of complexity, is when this added thing, just a few lines of code, include another argument, another parameter, and do the right, and modify the sum correctly when you want to include it or not. Oh, the program is 90% the same, 10% changes, and it's so easy to write, to get right. It took me almost no debugging. Okay, and then you want the yes, no, there's another level which brings it back down, and it seems almost trivial after all the work you've done with the in to remember where you've been in the recursion. That's all it's there for. It's really recording where you've been in your path. So the third level brings it back to basics. And it's sort of a nice set of 3 algorithms. If you understand those 3 algorithms, there's nothing more to understand really, with the minor thing that it would be nice to say, well, what happens when you've got negative numbers, for example? And for example, you may say, I want subsets which total to 0. Oh, that's interesting. You think to yourself, does it work? To be honest, I don't know what happens when you start putting negative numbers in there. I haven't even tried it. But it's not relevant because mostly the proposition or the problem is says that the elements of the array are positive numbers, I've noticed. Occasionally they talk about multi-sets, whereas a set, of course, has unique elements. So you won't get 2, 2, 2, 2 being a set. 2, 2, 2 is not a set. It's got to have unique elements. So 2, 4, 6 is a set, well, not 2, 2, 2. So you've got to have unique elements. Now, if you have multi-sets where the elements are not all the same, where the elements are all different, multi-set shouldn't probably make any difference, I reckon, but the negative numbers may cause some problems, which I researched. And maybe one day, in a future course, I might look on that as a 4th level and say, okay, let's bring in negative numbers here and see what it does to the algorithm. Because it does give you some more power, because subsets which total to 0, you could imagine may be interesting for certain applications. Okay, I think we can well and truly stop now, nice and on time for once. Thank you.
I really tried doing it. I still think it's
with the linear factor, I reckon you must something about this work.
taking it one by one. Finding the entire subset, then finding the curve.
What you're saying, you have to see it as a